Since the universe began, light has remained unchanged. Now man has created a new kind of light with powers and properties unlike anything that existed before. Laser light. Pulses of laser light can punch holes through a steel blade.
Come on. Okay, watch your
A
eyes.
continuous laser beam is a bloodless surgical tool, a light knife that burns away diseased tissue and coagulates blood before it can flow, leaving surrounding areas unharmed.
Look all right?
Okay.
You holding the uniform?
Yes.
Okay.
Laser light is so new, its full potentials lie in a world we have only begun to build. The laser, a light fantastic, a preview of tomorrow's technology. Man-made light, a forerunner of an increasingly man-made world, the world of the 21st century. The sun has always been the ultimate source of light for man. Across 93 million miles of space, it showers the Earth with light and heat to sustain life. The sun is a thermonuclear inferno. Its light is the product of atoms radiating energy as they jostle one another or break apart. Normal light is a product of such spontaneous atomic activity. Laser light is something new. Atoms in the sun emit uncontrolled light energy. The laser makes atoms emit orderly light. Its energy differs from normal light as much as a well-drilled army differs from a mob. The regimented light from a laser can be focused to a spot 250 billion times hotter than an equivalent area on the surface of the sun. The laser's unprecedented powers come from the nature of light itself. Light energy can be visualized as a procession of waves traveling at 186,000 miles per second. Light waves differ in frequency and intensity. We know these differences as the colors of the rainbow. Normal light sprays out in all directions, a jumble of many frequencies or colors, like the sound wave jumble we call static. A laser amplifies light wave energy and organizes it into an intense beam. A kind of light that doesn't exist in nature, coherent light. Coherent light waves march in step, like the sound waves of a pure tone. The laser is only 10 years old. In 1958, Charles Townes and Arthur Schawlow conceived the basic theories behind laser light. In 1960, Theodore Maiman created the first working laser device. At Stanford University, this reporter spoke with Arthur Schawlow.
There are already quite a large number of different kinds of lasers, and some of them, like the little one over here, are useful for all sorts of laboratory things, lining things up. It gives a straight beam of light, not very powerful. And it's very handy for educational purposes. You can show the properties of light in a very simple way. It isn't very powerful. You stick your hand in front of it and nothing much happens, although if you look straight at it, it really does look like a pretty bright thing.
What about more practical uses outside of the laboratory, the classroom?
Well, the same straight line beam is very useful for whenever you want a straight line. For example, there are machines now which will guide tunnel drilling machines. They won't drill the tunnel, but they guide and they shoot a laser beam, and the drilling machine rides the beam and stays and drills a straight tunnel.
Main power is on.
A beam of light is nature's straightest line. Light waves also vibrate at extremely high frequencies. This makes light an attractive medium for communications. The greater a wave's frequency, the more message information it can carry. Normal light waves are too disorganized to carry communications very far. A laser's organized waves are ideal. Theoretically, all of the world's present communications could be carried by a single laser beam. This is a laser communication system developed by Bell Laboratories. Normal television signals are converted into a code of electrical pulses. The laser light waves carry this pulse code. At the receiving end, the pulses are converted into normal television pictures. Today, we are far from filling laser light's 80 million channel capacity. By the 21st century, however, picture phones in every home and personal computers may demand laser communications. Despite its vast communications capacity, laser light is still light. Any obstacle can interrupt it, a human hand, a mountain, or clouds in the atmosphere. Messages carried by unprotected laser light would be in constant danger of interference. One solution is to create a laser pipeline. There remains the problem of guiding the beam in the pipe and keeping it in focus over great distances. Even the best glass lenses absorb some of the light and weaken the signal. Bell Labs scientists have come up with an ingenious solution to this problem, a lens, seen here in cross-section, that uses the density of air rather than the density of glass to focus the beam. An increase in air pressure increases air density. Changing the density focuses the laser beam as it passes through the air in the pipe. This communication system uses a continuous laser beam. There is a second form of laser energy, the short pulse. This laser at Corad Corporation is used to balance the rings of a gyroscope. A laser pulse lasting for 50 millionths of a second creates a 3,000 degree hot spot on the ring surface. This temperature vaporizes tiny bits of metal, correcting the balance of the ring. Pulse lasers have unique advantages as welding tools. In 3,000ths of a second, this laser welder can focus 5,000 degrees onto an area less than the diameter of a human hair. It creates a perfect weld. Chemical waste products are vaporized before they can contaminate the joint. Pinpoint accuracy is needed in the microscopic world of microelectronics. Tiny joints must be soldered without affecting adjacent heat-sensitive materials. The laser pulse melts the tips of these gold wires with a 1,000 degree hot spot. The temperature a fraction of an inch away remains unchanged. Every year, Western Electric produces 30 million miles of thin electrical wire for telephones. The wire is pulled through tiny holes drilled in diamond dies until it is 1/2 the diameter of a human hair. Drilling a microscopic hole in a diamond used to be a tedious day-long process, using steel pins coated with olive oil and diamond dust. A pulse laser has changed all this. The day-long drilling process has been reduced to a few minutes. The challenge with today's lasers is finding applications that are not simply glamorous new ways to do dull old jobs. The study of laser light is a science in itself. Today we use its most obvious properties. By the 21st century, laser light may find as many uses as electricity does today. The energy released by the most powerful pulse laser can be compared to Niagara Falls squeezed for a moment through a squirt gun. It takes about 200 pulses for this much less powerful laser to drill a hole through a diamond die. Drilling a hole in a diamond is a matter of carefully focused brute force. The unique characteristics of laser light offer far more subtle possibilities. The powers of laser light can be harnessed to heal as well as destroy. Using this anesthetized monkey, Dr. H. Christian Zwing studies the effects of laser light on the retina of the eye.
This OD?
Dr. Zwing and engineers from the Stanford Research Institute, working with the cooperation of spectrophysics, use a controlled blue-green laser beam to create tiny lesions on the monkey's retina.
3, 2, 1, 0, 1, 2. Very good.
This painless experiment shows how retinal tissue responds to laser light. It leads to a new way to treat human eye disease.
There's a lesion.
Dr. Zwang uses a high-speed motion picture camera focused through a microscope to record the laser impacts.
3, 2, 1, 0, 1, 2.
The lesion is the small white dot just below the center of the screen. Even as experimentation continues, Dr. Zwang and other ophthalmologists have successfully healed human eyes with laser light. This woman is suffering from a disease which causes the tiny arteries in her retina to leak blood into the retinal tissue, tearing it away from the wall of the eye. If the leakage continues, she will lose most of her vision. Photographs taken of the inside of her eye determine the position and extent of the disease. A harmless dye injected into her bloodstream makes the arteries appear darker in the photographs. The photographs reveal microscopic puddles of blood-saturated tissue. A pulse laser can stop the disease from spreading. After studying the photographs, Dr. Zwang begins treatment with the laser.
Now, Ms. Pierce, this is the laser right here. And you won't feel anything while I'm treating you. The only sensation you'll have will be a popping noise, and I'll show that to you now. Let you listen to it. Hear that? Fine. Now I'll show you the laser light on the ceiling. I'll fire it for you, and you'll be able to see the red light. Okay.
The red pulses create microscopic burns on the retina. The burns tack down the area around the leak so it can't spread.
That's 125 narrow beam. Look right up for me. Look over toward me. Over this way, Miss Pierce. Now hold it, hold it. And again. Excellent.
This post-operative photograph shows the diseased areas sealed after treatment with the laser. The pinpoint spot welds are permanent.
How can this beam create enough heat to do that job behind the eye without damaging the eye itself?
Well, I can show you that with an experiment, if you like. You know, we hear so much stuff about high-powered lasers and what sort of dangerous weapons they are that we had a little fun. We built up a little demonstration laser, which gives a certain fairly high power.
That's a dangerous-looking weapon there. Looks like a rocket gun.
Once we had a weapon, we had to have a suitable target for it. And just about that time, we went to the zoo and got a balloon for the children, and it turned out that there was a mouse in it. You know how mice get into everything. However, we had our more or less trusty laser, and we were able to dispose of it.
Now, tell me again how that happened.
Well, you remember the balloon, the mouse was dark blue, and therefore it's blue because it absorbs red light and transmits the blue. And so it absorbed the red beam from this laser, just a very short burst of red light, which furthermore was focused by the lens on the end of the laser. And so a little hot spot appeared where the light was absorbed, and that burned a hole in the inner balloon and started
Just like
breaking.
touching it with a lighted cigarette.
Right, but we could do it out here without going through. And this really does illustrate how they can do things with light now. It's not just something to look with, but you can do things and do them at places where you can see but not touch, as for example on the retina of the eye.
The laser could create a revolution in surgery. In a special laser laboratory at Cincinnati's Children's Hospital, Dr. Leon Goldman is studying the laser's healing power. Relatively simple operations like the removal of unwanted tattoos are another step toward discovering the laser's medical potential.
I'm putting on the glove to take my hand.
Color is the key to the laser's effectiveness. The dark color of the tattoo will absorb the red light energy in the laser pulse and be burned. The light-colored surrounding skin reflects the laser light and remains unaffected.
Tattoo will absorb the laser.
The laser impact feels like a drop of hot wax.
2, 1, go.
To the eye, the laser flash is 2,000 times brighter than the sun. Goggles protect doctor and patient from possible eye damage. The laser impact in slow motion.
2, 1, fire. Okay, Bob.
Turning up. Ready to fire. 3, 2, 1, fire.
Okay, that was good. All right, let's rest. Here's the result of your...
These burns will heal.
preliminary treatments.
If the treatment is successful, the tattoo will be gone. Similar results have been achieved with serious skin diseases.
Okay, Jim.
Ready for the laser kill?
This is the world's first laser operating room. Dr. Goldman uses a pulse laser suspended from the ceiling to treat skin tumors. Again, the laser's frequency or color is the key. The amount of tissue destroyed depends upon the length of the pulse.
Towards our right.
Laser surgery is still highly experimental. By the 21st century, a searing beam of laser light may join the scalpel as an essential surgical tool.
Okay. The quartz rod is now in position on...
A clear quartz rod guides the beam onto the tumor.
2, 1, fire.
The relatively small amount of blood reveals one of the laser's revolutionary surgical properties. The heat it produces is so great that blood vessels are sealed before blood can flow. A continuous laser beam has been used as a bloodless light knife, which cuts around the diseased area, sealing the wound as it goes.
Okay, ready.
Ready, Doctor?
Ready.
Ready? 3, 2, 1, fire.
Good. How's that feel? Well, I think, are those a little strong?
The actual length of the pulse is only 2/1000th of a second.
3, 2, 1, fire.
May I have the glasses off, please? Thank you.
Some forms of cancer have been treated experimentally with laser light. The results are far from conclusive. A few special cases are encouraging. 4 years after laser treatment, there is no trace of the skin tumor that once covered this arm.
With present-day lasers, then what reaches the target is light and heat.
They're the same thing, really. It's light, and when it's absorbed, it's converted to heat. We can show this rather graphically if we shoot a laser beam at a piece of paper that has something typed on it. The type will absorb, the black ink will absorb the light from the laser and convert it to heat. The white paper isn't affected because it doesn't absorb the light. The heat can be so violent that the ink is blasted right off the paper and you have erased the letter, but the paper is unaffected.
You have a demonstration of that?
I can do that. I have a rather laboratory, shall we say, model of a laser eraser, which I can set up here. A practical device, of course, would have to be and would be considerably smaller.
Well, practical use of that now, do you consider that this can be miniaturized and used actually as an eraser?
Yeah, people think of lasers as being wonderful military devices or exotic communications devices and think they'll have to cost a lot. But this is really a mass market. You know, there are some, I'm told, 5 million electric typewriters in this country, and they're manned by 5 million secretaries who can't spell, and that's a big market. Now, just to demonstrate how the laser eraser works, you see I've typed the word eraser on here, only I've misspelled it eresar. I won't even blame that on my secretary. But I'm going to take out that E that's wrong there. Let me just aim this. This thing in the nose here is just an aiming device. And we blast it. And you see it's gone.
By golly, it works.
It does. All we need to do is miniaturize it and get it into mass production. I think we've got something kind of useful.
What are your hopes of miniaturizing it, and miniaturizing it how far?
Oh, it could be built into the cover of a typewriter, for example, and aimed at the place where you type, and the typist would just bring the letter back to where it was typed and press the erase button, and it would be gone.
Well, now, isn't it possible to build a lethal ray gun? A ray gun just like this one we saw here?
Well, the science fiction writers, or newspaper reporters, they're sometimes known, like to make out something of that sort is the real purpose of all our laser work. But I don't think so far anybody knows how to make a laser that's big enough power and has enough sustained power to be a really useful death ray. Maybe someday it'll come, but it isn't here yet, I think.
This is what happens when a high-powered laser beam hits a granite slab at short range. By the 21st century, lasers may help dig tunnels by softening the rock ahead of the drills. The big problem with today's high-powered lasers is their inefficiency. 90% of the energy consumed by a laser like this is used to create the laser light. Only 10% is in the beam itself. In H.G. Wells' science fiction novel, War of the Worlds, Martians almost conquer the Earth with a sword of light. Today's lasers sometimes seem to have such destructive power. To do this job a mile away, however, requires more power than New York City uses in a year. At close range, a laser cuts asbestos like paper. But light is not only a source of heat and destruction, its energy reveals the world around us. Laser light can create a three-dimensional image so real you can see around it. This is the revolutionary new kind of photography called holography. At the University of Michigan, Yura Supatnieks prepares a hologram. Holography is lensless three-dimensional photography. There is no camera, no shutter, no lens, just a photographic plate, some mirrors and prisms, and a laser. To understand how a hologram is made, imagine a triangle. At its apex, a laser, at one corner a photographic plate, at the other the object to be photographed. First, the laser beam is split in two. One beam shines on the object to be photographed, in this case, models of two antique cars. The second beam shines directly on the photographic plate. The plate is exposed with reflected light from the cars and direct light from the second beam. This is the exposed plate. It is called a hologram. An eerie three-dimensional replica appears when a laser shines through the hologram, an image that seems almost as real as the original. Holography was originally conceived by physicist Dennis Gabor in 1948. But it took the invention of the laser's coherent light 12 years later before the first hologram was possible. Holography is the first totally new technology to develop from laser science. Today, its potentials are vast. By the 21st century, holography may be the key to full-color, three-dimensional motion pictures, or even 3D television. The future of holography is as exciting as the future of the laser itself.
Dr. Solo, what do you envision the uses of the laser will be by the turn of the century?
In some ways, I can't help thinking that the laser's not very much ahead of where the airplane was around 1910. It would fly. If you talked of crossing the ocean with 100 passengers at the speed of sound, people would think you're crazy, and you couldn't have done it no matter what you spent. Had to develop the whole science of aerodynamics, get rid of the wooden cloth and develop lightweight metals, and you had to have real inventions like the jet engine. Once you got off the ground, the rest of it had to come. Indeed, the lasers that we have now have gone a long way from our early ideas, and they'll go a lot farther. And I think they're going to be good and bad uses, but I hope that the good ones will outnumber the bad ones.
The laser today, in a sense, is a solution seeking a problem. It is here, but its real potential has not yet been realized. Its ultimate uses wait to be discovered. The creation of the laser was an ancient dream come true, the ray of light that heals, the sword of light that destroys your enemies. The laser today stands on a technological frontier, a frontier we are only beginning to explore. Where the laser's fantastic light will shine is a challenge we face as we move into the 21st century.